Welcome back to the start of Chapter 5. Chapter 5, Lesson 5.1, we're going to be talking about properties of exponents. Now, properties of exponents are things we should be familiar with already, and so a lot of the properties of exponents as we go through these should look somewhat familiar to you, although it does not hurt to brush up on these concepts and then actually apply them to some real examples. So first of all, we have to remind ourselves about a couple of things. Scientific notation is pretty common. We use that a lot in our science classes. Obviously, aptly named scientific notation. But we'll use that a lot. And it says a number can be expressed in scientific notation if it's in the form c times 10 to the n power, where c is between 1 and 10, and n is an integer. So again, a integer power, whether it be positive or negative, but it's got to be an integer power. Now they tell you that c has to be between 1 and 10. Another way to say that is you can only have one digit before the decimal point. Okay, and so when we start to write numbers from scientific notation to standard form and vice versa, it's helpful to remember that, again, to get a number that's between 1 and 10, you can't have more than one number before the decimal point. All right, so let's get into some of these actual properties and talk a little bit about how they work and, some examples of them. First of all, the product of powers property says that if you have the product of two things where we have the same base, we simply add the exponents. All right, so this becomes a to the m plus n because it's the product of a to the m times a to the n. The power of a power property says if I'm raising a power to a power, effectively this becomes a to the m times n power. And again, make sure you understand that this is not a times m times n. These are to the m times n power. And again, we'll get to some examples of these here shortly. The power of a product property says that if this is a to the n times b, both being raised to the m power, effectively that's a to the m power and b also to the m power. Now, it's not exactly the distributive property, but it kind of looks like it because both things in here get a power of m. Once again, it's not the distributive property. This is not what we would do if I had the sum, for example, a plus b to the m power. This is no good. We would not do it that way. A negative exponent property simply says that this becomes 1 over a to the positive m power. So anytime you have a negative exponent in the numerator, we put it to the denominator and make it positive. And then vice versa. Actually, if it's a negative exponent in the bottom, we move it to the top and make it positive. All right. The zero exponent property says anything to the 0 power is 1. Very, very, very common for a lot of people to think that a to the 0 power is equal to 0, and that's not true. A to the 0 power is 1. Quotient of powers property says that anytime we have the same base and we have these exponents here, we would take that to a to the m minus n. We subtract the exponents. Again, the bases have to match. And then finally, the power of a quotient property says that this is a to the m power over b to the m power. So both things get raised to the m power, both top and bottom. And I know that's a little messy and hard to read, but basically they both get an m power. So it looks kind of like this one, the power of a product. Power of a product and power of a quotient look an awful lot alike, and they really should. All right? So let's get into some practical examples here, and let's take a look at evaluating some of these things. First of all, this is 6 to the 2nd, then to the 3rd. That becomes the same thing as 6 to the 2 times 3 power, because anytime you have a power, we simply multiply. So that becomes 6 to the 6th power, and 6 to the 6th power is quite a large number, 46,656. All right, 4 to the 5th over 4 to the 3rd, remember, same bases. We simply subtract the exponents. This becomes 4 to the 5, take away 3, which is then 4 squared, and as we know, 4 squared is 16. And then finally, 7 to the negative 4 power. Again, anytime you have a negative exponent on top, we make that a positive exponent on the bottom. So this becomes 1 over 7 to the 4th power. And if you put 7 to the negative 4th power in your calculator, you're going to get some goofy decimal here. What I really want you to know is not to plug it into your calculator, but instead recognize that this is 1 over 7 to the 4th. Now use your calculator to get 7 to the 4th. Okay, 7 to the 4th happens to come out to 2,401. And so because it's negative 4th, it becomes 1 over 2,401. All right? So again, just simply plugging that into your calculator, 7 to the negative 4th power, you're going to get something kind of funky there. So you're going to have to be familiar with those properties and how they work. Let's take a look at using scientific notation. It says Iceland covers about 1.03 times 10 to the 5th square kilometers and has an approximate population of 2.94 times 10 to the 5th people. About how many people are there per square mile? So again, we want people per square kilometer. Sorry, I said square mile. People per square kilometer, so again we want people on top and then kilometers on the bottom, or square kilometers on the bottom. So again, you want population over land area. So your population is 2.94 times 10 to the 5th. This is 1.03 times 10 to the 5th. And the quotient of powers property says for this is going to become simply 2.94 over 1.03. We'll deal with that in a second. And then 10 to the 5th over 10 to the 5th becomes 10 to the 5 take away 5. And as we know, 5 take away 5 is 0. So the zero power property says anything to the 0 power is the same thing as 1. So this whole last term effectively just becomes 1. So this is 1. And so 2.94 over 1.03 times 1 is simply 2.94 over 1.03. Using a calculator, we get 2.85, again, times 10 to the 0 power, which is the same thing as 1. 2.85 times 1 is 2.85. And so basically it says there are about 2.85 people per square kilometer in Iceland. Obviously not a very densely populated area. All right. So let's continue with our simplifying expressions idea. We're going to work through a couple of examples here in which we're going to be using our power properties to simplify some expressions here. First of all, when we have a power of a product, this becomes, well, this is kind of 2 in 1. This is the power of a product, and it's also power of a power. And so this becomes x to the 5th to the 3rd power times x to the 2nd to the 3rd power. So what they're saying, this is the power of a product. Well, each of these things in the product gets raised to the 3rd power. So like I said, that kind of looks like the distributive property. And then on top, this is then power of a power. Power of a power says we multiply these two together. So this becomes x to the 15th power. And then, sorry, I got to go back up here and fix this. I don't know why I wrote a y here. It's supposed to be a y there. And so this becomes y to the 2nd to the 3rd, which is y to the 6th. So we have x to the 15th times y to the 6th. And then the quotient of powers property says that this is x to the 15 take away 15 times y to the 6 take away 8. And again, we take those things that have the same bases and we subtract their exponents. Those things that have the same bases and subtract their exponents. Now 15 take away 15 is simply 0. So this is x to the 0 power times y to the, and then 6 take away 8 becomes negative 2. The zero product property tells me that this is 1, right? And so this is just simply 1 times y to the negative 2. And then as we know, a negative power becomes a positive power on bottom, so this is 1 over y squared. All right, let's try another example. Another example says this is a to the negative 4 squared over b squared. Now, understand that there's a lot of different ways you can do this. In the book here, they first say let's do the power of a quotient property. We actually could do this a number of different ways. I'm not going to go through all the examples in the video here, but certainly you could do this a number of different ways. So your first step doesn't really have to be this, as long as it uses one of the properties, and I'll kind of explain that in just a moment here. Anyway, a to the negative 4 to the 2nd becomes, again, second power. That's power of a quotient because both things get a second power. This becomes a to the negative 8. This becomes b to the 4th. And then a to the negative 8, since it's a negative power on top, it becomes a positive power on the bottom. So this becomes 1 over a to the positive 8th. And then b to the 4th, since this is b to the positive 4 on the bottom, it stays where it is. If it by chance happened to be a negative power on the bottom, we'd move it back to the top. Now what I was talking about before is there's another method you could probably use here. Again, we could use our negative exponent property. We could use that first and say this is the same thing as 1 over b squared times a to the positive 4th, because again, the negative exponent on top becomes a positive on the bottom. And then everything in here gets a second power. That's power of a quotient property, so this becomes 1 squared, which is 1. And then b to the 2nd squared becomes b to the 4th. A to the 4th squared becomes a to the 8th. And so you could have it that way as well. Both of those are certainly adequate means of solving that problem and simplifying that particular expression. So, a few checkpoint problems here. All right, go ahead and pause your video and try these, and we'll be right back with solutions. Now, as I was saying before, there are many different ways to try this particular problem. You could do the power of a quotient property first. We could simplify inside of here first. I'm a big fan of simplify first if you can. So if there's any simplifying you can do first inside of there, I'm going to try to do that first because that's going to save me some time in the long run. And so my first suggestion is, if you can, simplify first inside of those parentheses. So this becomes 8 to the 5 take away 2. Again, that is the quotient of powers property. We have the same base, and so we subtract the exponents. This is still to the negative 1 power. This becomes then 8 to the 3rd power, still being raised to the negative 1. Now, power of a power says that this is 8 to the 3 times negative 1, which is negative 3. And then because it's 8 to the negative 3 on top, it becomes 1 over 8 to the 3rd on the bottom. From there, 8 to the 3rd power comes out to be 512. And so this is 1 over 512. All right. Here's a scientific notation problem. Remember, we can just multiply the integer values first, 4 times 7, and then multiply the properties, or multiply the powers on the end. So we can switch the order of multiplication. Again, if it's multiplied, we can just change the order to do it any way we want to. So this becomes 28 times 10 to the 3rd times 10 to the negative 2. And again, 3 take away 2 is simply 10 to the 1st power. So it's 28 times 10 to the 1st power. We can write it in scientific notation. Again, we have to put the decimal point between those two numbers, and that's a result of making it 1 power of 10 bigger, because again, this becomes 2.8, and to get 2.8 back to 28, we have to add another power of 10. Basically, we have to add 1 place value. So 2.8 times 10 to the 2nd power is one way we could write it. And obviously, if you just simplified this, 28 times 10 is also 280. So that's another, there's a couple different means for that one. As I said, I'm a big fan of simplify first. Since this is y to the negative 6 on top, I'm going to make it y to the positive 6 on the bottom. And now this is being raised to the 7th power. Remember, this is the power of a quotient, and so x squared to the 7th power over y to the 6th to the 7th power. And then x to the 2nd to the 7th becomes x to the 14th. Remember, that's power of a power. So anytime I'm raising a power to a power, I multiply those exponents. This is x to the 14th over y to the 42nd power, because 6 times 7 is 42. All right? This is kind of a mess here. It should say 14. All right, and then finally on our last example, like I said, simplify first if you can. First of all, b to the 1st over b to the 1st. Well, b to the 1 take away 1 is 0, right? So that's b to the 0 or just a 1. Or anytime you have the same number top and bottom in a fraction, you just cancel them out. So I'm just going to get rid of the b so I don't have to mess with those. This is negative 2, and then a to the 2 take away 5, all being raised to the 3rd power. Well, 2 take away 5, as you know, is negative 3, so this is negative 2 over, negative 2 a to the negative 3rd, still being raised to the 3rd power. Now if I could then, because this is negative 3 on top, I want to make it positive 3 on the bottom, so this is negative 2 over a to the 3rd, still being raised to the 3rd power. And now basically you cube the top and bottom. Negative 2 cubed is negative 8. On the bottom, a to the 3rd becomes a to the 9th, because again, it's power of a power, so we're going to multiply 3 times 3. So it's negative 8 over a to the 9th power. It's kind of hard to tell the difference between my a and my 9, but that's what you got. All right? And our last example here, to close out the lesson, is wants to compare real-life volumes. Obviously, we know that the volume of a sphere the volume of a sphere from our geometry classes in the past is 4/3 pi r cubed. So we'll be using that formula to figure out the volume of our beach ball and our baseball. All right. So it says how many times as great as the baseball's volume is the beach ball. So we want to compare the beach ball to baseball. So when we set up our proportion, we want beach ball over baseball. Obviously, the volume of the beach ball is larger than the baseball, and so if you think about those two quantities, beach ball being much larger than a baseball, it's going to have a bigger volume. So this number should be something larger than 1. It says the radius of a beach ball is about 5.6 times greater than the radius of a baseball. So if r equals the radius of a baseball, then the radius of the beach ball is 5.6 times r. And so we're going to plug that in right here, 5.6 times the radius of the baseball, where r is some arbitrary radius of that baseball. Now we don't know the actual radius of that. Again, we're just going to get the number of times larger it is. Now look at 4/3 pi over 4/3 pi is going to cancel out. So basically these two quantities cancel, and I end up with 5.6 r to the third over r to the third. All right, so this is still 5.6 r, all being raised to the third power. All right. All right, now the power of a product property tells me that both of these get a third power. So this becomes 5.6. Let's see if I can move that out of there. This becomes 5.6 to the third and r to the third. Now 5.6 to the third power, we're just going to leave that as 5.6 to the third right here. 5.6 to the third. And then we have r to the third over r to the third. Well, same base, right? Same base, and so we subtract the exponents. This becomes r to the 3 take away 3, which is 0. Now, anything, the zero product property says anything to the zero power, r to the 0 is equal to 1. Remember, anything to the zero power is 1. So this simply becomes whatever 5.6 to the third power is, right? And 5.6 to the third is about 176. Again, it's an approximate here, something other than that. So the beach ball's volume is about 176 times larger than the baseball's volume. That concludes our lesson for 5.1. Again, these are all properties that we've done in the past in previous algebra classes, and so really now it's just a matter of reviewing them and using them for solving these particular, or simplifying rather, these problems.